Okay, guys, the name of the section that we're going to be discussing today is called Putting Numbers in Perspective. Okay, so we'll talk about some things like scientific notation, we'll talk about scaling, other things that have to deal with putting numbers in perspective. Okay, so sometimes in our world, we will talk about extremely large numbers, such as populations or the national debt. And then sometimes we'll also talk about extremely small numbers. For example, the weight of a cell or weight of a part of a cell or something. Now, one thing that we can use to simplify talking about these numbers is what's called scientific notation, right? So it's a format for writing either very large or very small numbers in which we use powers of 10 to make the writing easier, right? So if I wanted to write this extremely long decimal, I could write that as 5.43 times the power of 10, right? And if I wanted to write 38 million, I could write that as 3.8 times the power of 10. So it's sort of cutting down on the writing that you have to do in order to produce this number. Okay, so let's talk about first converting from standard notation to scientific notation, right? So the first thing you want to do is you want to move the decimal point so that it comes after the first non-zero digit. And we're going to do an example, a couple examples of this in a second. Now for the power of 10, you're just going to use the number of places that the decimal point moved, right? The power is going to be positive if you move the decimal to the left, and it's going to be negative if it moves to the right. All right. So for example, let's look at 3042. Now, right now, the decimal's right here, right? If you don't see it, it's at the end. Now, if I want to move this so that it comes to the right after the first non-zero digit, I need to move it 1, 2, 3 spots to the left. And when I do that, the number would then be 3.042. All right, now I need to multiply that by 10 to the appropriate power. Well, since I moved it to the left 3 spots, that means that my exponent is going to be a positive 3. Right? Now, the way that I always like to think of it is this power should be positive if you need to make the number bigger to get back to where you started, right? So I need to start with, I started with 3042. So I would need to make 3.042 bigger, so then the power should be positive. If I wanted to make it smaller, then I would need a negative power, which we'll see in the next example. Now, in the next example, we have 0.00012. Right? So of course, now the decimal's right there. So I need to move this decimal 1, 2, 3, 4 spots to the right, and that will give me a 1.2. Right? So now I have 1.2, and then the power of 10 that I need, of course, is a 4, and it needs to be negative because I moved it to the right. And then, of course, if I were to multiply that out, since it's a negative 4, I'm making the number smaller, right? So it makes sense that that power is negative. Now, for the last example, we have 226 times 10 squared. Right? Now, it might look like this number is already in scientific notation, but it's not, right? And that reason why is because our number is not between 1 and 10. So what I'm going to do here is my decimal for this part is right here, and I need to move it 1, 2 spots to the left. So this part right here is going to become a 2.26 times 10 squared since I moved it to the left. But then I still have this 10 squared that I started with, right? So I need to combine these two somehow. Well, if you remember your rules for exponent, if you multiply two things together that have the same base, we add their exponents, right? So this is going to become a 2.26 times 10 to the 2 plus 2, which is 10 to the 4th. All right, so that's that example. Okay. Now let's talk about how to go the other way. How do you convert from scientific notation to regular standard notation, right? Now, of course, the way that we do this is we look first at the power of 10, right? That power of 10 is going to tell you how many places to move your decimal point, right? Now, if the number is positive, you're going to move it to the right, and you're going to move it to the left if that power is negative, right? And then, of course, if the decimal point creates open places or, you know, large digits, I shouldn't say large digits, I should say if you have a large number of digits, then you can put in commas also, right? So for example, if you want to do 4.01 times 10 squared, well, that decimal place, sorry, that exponent is positive, so I need to move this decimal place 2 spots to the right. So of course, this would give me a 401. In the next one, I have a 3.6 times 10 to the 6. So I need to take 3.6 and move it to the right by 1, 2, 3, 4, 5, 6 spots. And all of these empty spaces I'll fill in with zeros. So it looks like I'm going to have a 3,600,000. Right, and then last but not least, I have a 5.7 times 10 to the negative third. So I need to take 5.7, and since it's negative, this time I'm moving it the other way. So 1, 2, 3 spots. So of course, we'll fill those in with zeros. So this is going to become a 0.0057. All right, so that's converting from scientific notation to standard form. Okay, so let's look at another example. So in part A, we have that the total spending in the new federal budget is 3, and I guess this is trillion, 900 billion, and then we have all these zeros. Well, right now, the decimal's right here. So I need to move it. This would, of course, be 3 spots, 1, 2, 3, another 3 spots, another 3 spots, and another 3 spots. So that's 3, 3, 3, 3. So a total of 12. So this is going to be a 3.9 times 10 to the 12th. And of course, we're making the number bigger. If I want to go from 3.9 to 3 trillion, I need to make it bigger, so we use the positive power. Now in part B, we have the diameter of a hydrogen nucleus, right? So we have point, and let's see if I can count these zeros right. So it looks like we have 1, 2, 3, 4, 5, 6, 7, 8. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 zeros. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then 1. So now I need to move the decimal this way. We need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 spots to the right. So this is going to be a 1 times 10 to the negative 16. All right, so that would be that example. Okay, now to multiply or divide with scientific notation, we're going to make this easy on ourselves. All right, so let me show you what I mean by this. So we have 6 times 10 squared, and I want to multiply that by 4 times 10 to the 5th. Now, the way that we're going to handle this is we're going to rewrite this, right? Now, it doesn't matter the order that we multiply numbers. If I do 2 times 3, that's the same as 3 times 2. So we're going to write this as 6 times 4 times 10 squared times 10 to the 5th. Now, 6 times 4 is 24. And 10 squared times 10 to the 5th, if we just add those exponents, we're going to get 10 to the 7th. Right? Now we're close. We just have to fix this 24. Right? So that just needs to go 1 spot to the left. So this is 2.4 times 10 to the 1st times 10 to the 7th. So finally, this will give me a 2.4 times 10 to the 8th. Okay. And then last but not least, we have a 4.2 times 10 to the negative 2 over an 8.4 times 10 to the negative 5. Right? Now here we're going to sort of use the property that if you multiply fractions, you can break them up, right? Because you're just multiplying the numerators together. So as long as you keep the numbers on top, you're okay. And multiplying the denominators together. So I can separate this as 4.2 divided by 8.4 times 10 to the negative 2 times 10 to the negative 5, right? Well, the way that we do this is we do 4.2 divided by 8.4, and that's 1/2 or 0.5. And the way that you handle negative exponents is that this would become a 10 to the 5th over 10 squared, right? You just switch their positions. And then this would become 10 to the 3rd. So now I just need to fix this. I need to move it one spot to the right. And it's 5 times 10 to the negative 1 times 10 to the 3rd. And this would give me a 5 times 10 squared. All right, so that's multiplying and dividing. So you're essentially just grouping the regular numbers together, grouping the powers of 10 together, doing those separate, and then if you need to, you fix that number at the end. Okay. One other cool thing about scientific notation is that you can use it to approximate how much an answer makes sense, fairly quickly without finding the actual value, right? So in this example, we say that you and your friend are doing a rough estimate of how much garbage New York City residents produce each day. So you estimate that on average, each of the 8.3 million residents produces about 1.8 pounds or 0.0009 tons of garbage each day. So then the total amount of garbage would be these two things multiplied together, right? So a friend tells you that 225 tons is the answer, right? Now we're going to determine if this answer is reasonable using scientific notation. Now, 8.3 million, or sorry, 8,300,000 is 8.3 times 10, and this would have had to move 1, 2, 3, 4, 5, 6 spots. So this is 8.3 times 10 to the 6. Now the other one is 9 times 10 to the, in this case, 1, 2, 3, 4, negative 4. Right? So now if I do 8.3 times 9, that's going to give me, so 8 times 9 is a 72, and then 0.3. So I'll do this a little bit more thorough, I guess. So I want to do 8.3 times 9, and that will give me a 74.7. Now the powers of 10 will end up giving me a 10 squared, right? So of course, this gives me 74.7 times 10 squared, which is like 7470 tons, right? And the idea here is that this is, of course, a 4-digit number, and your friend said a 3-digit number, right? So this answer really isn't that reasonable, right? Because based on this calculation, we're getting something that's much, much larger than what the friend told you, okay? So that gives you a way that you can sort of quickly see if an answer makes sense or not. Okay. Now, sort of in the same breath here, we can say that we can use scientific notation in an order of magnitude estimate, right? Now, of course, an order of magnitude estimate basically is going to suggest only like a broad range of values. Like it's not going to be very specific, right? So for example, make an order of magnitude estimate of total annual spending on ice cream in the US. And we'll assume that there are approximately 300 million people in the United States. So 300 million people. So let's say on average, Americans spend let's say $20 a month on ice cream. Right, and of course you can make that more or less depending on your how much you think that Americans like ice cream, but we'll just say $20 per month. So then $120 per month means that I need to multiply that by 12, And that gives me $240 per year. Right? So then I'm taking 2.4 times 10 squared for the $240 per year, and I'm multiplying that by 300 million people, which would be 300 with 6 zeros after it. So then this would be times a 3 times a 1, 2, 3, 1, 2, 3, 4, 5. So it looks like we get a, and that was said completely wrong. It should be 1, 2, 3, 4, 5, 6, 7, 8, right? So it's times 10 to the 8th. So this would give me a 7.2 times 10 to the 10th, right? So then that would tell me that I can expect to spend on average 7 and then 2 with what, 9 zeros after it, right? So then I would have 2, 2, 3, 1, 2, 3. So it looks like something like this. $72 billion, right? So if we use this estimate, we could say that around $72 billion is spent by Americans on ice cream. So that's sort of an interesting problem to do. Okay, now here's sort of a cool problem to do here. Let's consider if we have $100 billion, right? Now, of course, this is a lot of money, but we want to know just how much is it, all right? So let's assume that if we want to account this amount out with $1 bills, all right? So assume we have this in all ones and it takes 1 second to count each bill. How long would this take? Well, of course, it's going to take 100 billion seconds. Right? So one way that we could sort of handle this problem is if we have 100 billion, right? Well, then we can say if this is in seconds, how do I go from seconds to minutes? Well, we could say that this is 60 seconds in 1 minute. And let's put it in hours just to make it a little bit more doable. So let's say this is 60 hours. Sorry, 1 hour. Sorry, I had it right the first time. Let me put my minutes down here. So 60 minutes in 1 hour. And let's go ahead and let's make it days while we're at it. So 24 hours in 1 day. Right? So if I take 100 billion and I divide it by 60 times 60 times 24, that will give me how many days it will take to count out this money. So if we do that, okay, and then divide it by 60 times 60 times 24. And if you're following along and you're doing this in the calculator, make sure that all those bottom numbers are in parentheses. Well, this would take 115,747.407 days, right? Now that's a lot of days. So let's talk about, well, how long would that take in weeks, right? So if we wanted to get this to weeks, well, there are 7 days in 1 week. So I would need to divide this now by 7. Now, if we do that, if I add in a 7 there, then we're still 165,343.91 weeks, right? If I add a 52 in there, then that would give me how many years it would take. So if we add in a 52, it would take 3,179.69 years to count out this money. All right, so you can sort of have fun with that example, but that just goes to show you how much money $100 billion really is, right? It's just quite an extraordinary amount of money. Okay, So let's move into another example. So we want to compare the US population, which we're going to assume to be 300 million people, to the world population, 7 billion, right? So let's do that first. So for the world population, right? So we have that the US population over the world population is going to be 300 million over 7 billion, right? Which we could do in scientific notation. This would be a 3 times a, let's see, and if I add a million to that, so I would need 10 to the 8th, I believe, right? And if we have a 7 billion, that's 7 and then times 10 to the 11th, I think. Let me just double check that. So if I do a 300 million, I think I'm messing that up. So 300 million would look like this. So I need to go 1, 2, 3, 4, 5, 6, 7, 8. So that part's right. And then 7 billion, I actually think I'm going to need 3, 6, 9, just 9 here. Yeah, I was sort of getting messed up because I had 3 and not 300. Right, so this will give me a 3 over 7 times 10 to the negative 1. And if we do that 3 over 7, right, we're going to get a 0.4285 times 10 to the negative 1. And of course, if I move this over, I'm going to get a 4.285, and I'm going to need times 10 to the negative 2. All right, so that's sort of a number that's going to compare the US population to the world population. Now, if we look at the energy consumption, right, we want to do 1.0 times 10 to the 20th over 5.3 times 10 to the 20th. All right, well, these powers of 10 just cancel. And if I do 1 divided by 5.3, I'm going to get a 0.18868, roughly. And then, of course, once I move it, I'm going to get 1.8868 times 10 to the negative 1. Now, this number is a whole order of magnitude bigger than the world population. So what does this mean? This means that the US energy consumption is much more than the average usage worldwide. Otherwise, it would be closer to just the population. All right, so that's sort of an interesting example to look at. Okay, now I believe that the last thing that we talk about in this video is the idea of scaling, right? So there are multiple ways that you can sort of use this, right? So for verbal scales, you have, for example, you can describe something in words, like you have 1 centimeter represents 1 kilometer, right? Now, most of the time, this usually means that if you're looking on a map, 1 centimeter on the map represents 1 kilometer of actual distance, right? Sometimes you'll even see this marked using a graphic on a map, right? And a lot of times this is even used in ratio form, right? So you can say that there's a scale ratio of 1 to 100,000, right? Using the fact that there are 100,000 centimeters in a kilometer, right? So for the last example, we'll say that a city map states that 1 inch represents 1 mile, right? And we want to know what is the scale ratio for this map, right? Now, when we say scale ratio, we need to come up with something like this, right? So we need to figure out, well, how many inches are in 1 mile, right? Well, there are 5,280 feet in 1 mile, and there are 12 inches in 1 foot, right? So for example, if I want to say that I have 1 inch per 1 mile, and I want to express this as a scale ratio, then I need to go from, I need to convert miles to inches, right? So 1 mile, and I would need to multiply by 5,280 feet, so my miles cancel, and then I need to multiply by 12 inches over 1 foot to get my feet to cancel. So then if I multiply 5,280 by 12, I get 63,360 inches in 1 mile. So then that would be your scale ratio. All right. Now, if you're interested in looking at some other examples, you can look in the textbook on pages 144 through 146. But other than that, that concludes this video on putting numbers in perspective. I hope you enjoyed it, and I'll see you next time.